is April the 21st. So that means like it just goes as a W. It doesn't end up hurting your grade. So I want to make sure that this gets graded, put into Moodle so that you can look at all your grades and kind of make a decision if you need to. Thought somebody had their hand up. Oh yeah. Yeah, you get a note page, so it'll be fine. Okay. All right. Okay, so this is chapter 9. So in chapter 9, there's a couple of things that we need to talk about. So acids and bases, characteristics of acids and bases, identifying acids and bases, and then we're going to talk about equilibrium. From there, we can talk about pH. So pH is just a way of being able to measure the amount of acid or base that's present in a solution. So this all started off quite a long time ago. So this is like 1600. So this is kind of like gas law old, okay, versus like some of the newer stuff like the radiation chemistry. So there was a Swedish chemist, Arrhenius, and he was the one that really first described the fact of what acids and bases do. And he really defined them according to what happens when you put them in water. So he said if you put an acid in water, it will split into ions. That term is called dissociate. So just think dissociate means to break apart. So it breaks apart and forms ions. The ions that are characteristic for an acid are called hydrogen ions. So H plus is a hydrogen ion. So you can think if you took HCl, which is hydrochloric acid, and you put it in water, it is a strong electrolyte. Remember that we used the light bulb apparatus. HCl was one of the things that we tested. When I put the beaker up of HCl on that light bulb apparatus, it was bright light bulb because 100% hydrogen ions are formed and chloride ions are formed. So that H plus is what he defined. Hydrogen ions typically combine with water molecules. So if it's in a solution in aqueous, H plus aqueous is also commonly seen as H3O plus. All that's saying is that the water molecules actually can take that hydrogen ion. So if you see H plus or H3O plus, it's saying the same thing. Okay, so H plus aqueous and H3O plus aqueous, they're the exact same description or the exact same. Don't let that throw you. Okay, so if you see this or you see this, then you know that means that that's a hydrogen ion and characteristic of an acid. Other things about acids. So most of the time people think of something that's acidic. You think of something like vinegar. Think about lemons, limes. They're very sour. They have like a tart, sour flavor to them. Acids are commonly added to dishwashing liquids. So you might have like the Dawn with lemon juice in it. And that's because lemon juice is acidic. And so it actually helps in dissolving grease. Acid is formed in clouds when nonmetal oxides combine with water in a rain cloud. So when we look at pH, you will see that rain is not completely neutral. Rain is always slightly acidic. And that is because of nonmetal oxides like sulfur dioxide that's just in the air, typically formed by industry. It's kind of like a waste gas that's produced when you burn stuff. Well, that sulfur dioxide combines with moisture in the clouds and creates this acid rain. So it's not terribly acidic, it's just a little bit acidic, but any acids in water, when they contact metals, slowly over time, they will actually react with metals, dissolving the metals and produce hydrogen gas. So this is one of the reasons that for the last, I think it's just about done, but the Statue of Liberty went through like a 4-year facelift. And the reason that they had to do it is because the rain over the 150 years that it's been in place, that rain has slowly started to like wear that statue away. So that's common in old statues, is they actually have to go back and like resurface it because her nose was getting a little flatter over time. And that's just because of the slight acidity that the rain has. So rain will cause damage to statues. It's just another characteristic, something that acids can do. So these are sort of general things. Well, in the early 20th century, these two scientists, Bronsted and Lowry, they were looking at acids, and instead of just looking at like what acids do when you put them in water, they were really trying to define, well, what do acids do in a reaction? So rather than just what happens when they dissolve, like what Arrhenius was talking about, HCl, you put it in water, it makes hydrogen ions. But they found that anytime an acid is involved in a reaction, that it acts as a proton donor. So acids like to give their protons to other things, which makes sense. Like if you look at the acids or hydrogen ions are produced in water. So that means that in a reaction, if an acid is in a reaction, you will find that the acid is going to lose its hydrogen ion. So that's an easy way of trying to like define, oh, this is the acid versus the base, because acids will lose their hydrogen ions in a reaction. So here's the example just like I told you, like if you see this, you know that's a characteristic of an acid, seeing that H plus or hydrogen ion. But if you see H3O plus, that is the hydronium ion, that's also that characteristic of an acid. So just remember, they're really talking about the exact same thing. Because I know sometimes people see H3O plus and they're like, what's that? It's just saying that it's the acid that's in water. So just so that you know, those two are exactly the same. Bases. So Arrhenius took and studied bases and found that bases have a little bit, in a way, they're like the opposite side of the coin of the acid. So bases, they taste bitter. Acids taste sour, bases taste bitter. An example, like coffee, has some basic flavorings in it, so it has kind of a bitter taste. Espresso has an even stronger bitter taste. Unsweetened tea, people kind of describe it as having a bitter taste. A lot of herbs like basil, thyme, oregano, they kind of leave this weird taste on the back of your throat. Also bitter. So those are those bittering types of agents that they've got. The other thing though, remember when I said that acids dissolve grease? Bases actually like leave a slippery feel on your skin. So if you've ever been swimming in the ocean, you know how your skin feels really slippery when it's wet as you're swimming along? So that is because the ocean is slightly basic. So it's not a strong base, but it's slightly basic, which gives it that characteristic feeling. So while Arrhenius said that hydrogen ions are made by acids, he found that bases, and we can use sodium hydroxide, for example, which was another strong electrolyte. When you put sodium hydroxide in water, sodium ions, Na+, and hydroxide ions are produced. So that OH- was characteristic of a base. So then on come Bronsted and Lowry, come in later and say, okay, so those are characteristics of a base all by itself, but what does a base do when it's in a reaction? So while acids are proton donors, they always lose their protons. Bases act as proton acceptors. So in a reaction, the base will gain a proton, typically taking it from the acid, but that way you can recognize the acid and base reactions that occur. So this one just shows what happens when you put sodium hydroxide in water. So you see that they split into their ions, sodium ions, and then those hydroxide ions. So you remember the hydroxide ions were one of your polyatomic ions. So in this top reaction, if you take HCl and you put it in water, looking at this reaction, HCl and its most common product. Okay, so remember how we did this with oxidation and reduction? You looked at the reactant side and looked at like the most similar product. What is the thing that looks the most like that reactant? So HCl and Cl minus. Do you see that it loses its H? Goes from HCl to Cl minus. So we say, okay, this loses its hydrogen ion, and that is that characteristic to describe an acid. Just like oxidation reduction, you always describe the reactant as an acid or a base. If you look at water in this one, following across, you see that H2O and H3O plus are the most similar. So in comparing reactant and product, you can see then that water gained hydrogen. It gained a hydrogen ion. That means it's a base. So acids are always going to lose hydrogen ions. Bases are always going to gain. So look at the bottom. Go ahead. Right, so if you look at water on the left, and then you look at H3O plus on the right, how has it changed?
The 3 and the plus.
So it's gained a hydrogen. Can you see that? So it went from H2O to H3O.
Okay.
So it gained a hydrogen. So you're really looking at the start and the end and asking yourself, okay, well, did it gain or did it lose a hydrogen in a reaction? Because that's all that acids and bases are going to do. So we don't have to worry about swapping of oxygen or electrons or any of that. It's really just going to be this changing or swapping of hydrogen that characterizes that acid or base. So you look at the bottom one and you tell me, one, what is the most similar pair to NH3? NH4. Everybody in agreement? Okay, so when you look at the first two, look at the two reactants, look at the two products, do you see NH3? NH4 is the most similar. So what happens to NH3 then? Does it gain or lose? So then you'd say, yes, this gains hydrogen, right? Because it goes from NH3 to NH4. So if it gains hydrogen, this is a base. Now in this one, water is still participating in this reaction, but the water in this reaction goes from H2O to OH minus. So what happened to it? It loses. Okay, so just look at the reactant side, then the product side. You're just comparing the most similar pairs, whether they gained or lost a hydrogen ion. You can really just look for the hydrogen. So you can see that this one loses its H plus. That makes it an acid. But again, notice that we identify it over on the reactant side, just like what we did with oxidation and reduction. It was always the reactants that got identified as being oxidized or reduced. But notice in this, water, depending on what the reaction is, sometimes water is a hydrogen acceptor. Sometimes water is a hydrogen ion donator. So it can actually, water can participate as being an acid or a base depending on what the other molecule is in the reaction. So you can't just look at water and say, oh, it always acts as an acid, or oh, it always acts as a base. You really have to look at what happens to the water molecule. In the first one, it gains a hydrogen ion, which makes it a base. In the bottom one, it loses a hydrogen ion, which makes it an acid. So it actually has this like ability to do both, depending on what the characteristics in the reaction are. So ones that we've talked about, ones that you should see and be somewhat familiar with in a formula. These three acids and these two bases. So sulfuric acid, H2SO4, hydrochloric acid, HCl, and HNO3, which is nitric acid. So I will tell you, we used all of these in lab. We didn't really use nitric acid except once in the entire semester, but we used sulfuric acid that was in that little brown bottle. We would get like just a few drops, stayed in the fume hood. Concentrated hydrochloric acid stayed in the fume hood. But in the acid and base, the antacid lab that you did, you actually had a Erlenmeyer flask, like a big flask, of hydrochloric acid that was on your lab bench, but remember it was diluted. It was only 0.1 molar, so it wasn't really concentrated solution. Sodium hydroxide, that is what we used when we made soaps. Okay, so that was that kind of thick 6 molar sodium hydroxide, so it's pretty concentrated what we added to the fat or oil soaps. Potassium hydroxide you haven't used, but it is another one that's a pretty easy one to remember in terms of being a strong base. So all of these, both of these are strong acids and bases. So remember, strong means it's like a strong electrolyte. So it dissociates 100%. So you have, when you put hydrochloric acid in water, you get 100% ions, 0% remains associated. So the big important thing about in remembering with this is that strong acids and bases, strong acids are going to make a lot of hydrogen ions. Strong bases are going to make a lot of hydroxide ions. So if we were using concentrated forms, I always put them in the fume hood, and this is why. Strong acids and bases are very reactive. That means that they want to give their hydrogen ions or pull hydrogen ions from other things. So they want to react to become more stable. This reaction with body tissues can cause damage. So this can cause a chemical burn. So if you got sulfuric acid on your skin, didn't rinse it off, you would start to notice it would get red, it would get irritated, and it would actually begin to damage through layers of the skin. And you can get a 1st degree, 2nd degree, even a 3rd degree burn from a strong acid or base. So they call that corrosive. So if you see chemical bottles that have that term corrosive, corrosive really means that it's reactive with body tissues. And so you want to keep some kind of barrier between your skin and that chemical. Okay, whether you're just using small amounts of it or maybe you have to wear gloves. We'll talk a little more about some of the stronger acids and bases in pH. But that's what that term means. The term corrosive just means that it's reactive with body tissues. But now there's the weak ones too. So just like there's strong electrolytes, there's weak electrolytes. And in fact, vinegar is the one that we tested when I brought the light bulb apparatus down. So remember, in this, the arrow is actually wrong because this arrow goes both directions. So a weak acid separates into ions to a small degree. So only about 5% of the acetic acid molecules form ions. 95% remain as a whole molecule and do not produce hydrogen ions. So when you're talking about things that are weak acids, since they don't make a lot of hydrogen ions, remember that this is the same as a hydrogen ion, H3O+, since they don't make a lot of ions, they're not as reactive. So this is why, like, you put vinegar on your food, right? So you wouldn't put hydrochloric acid on your food because that strong electrolyte would cause damage to body tissues. But weak electrolytes, weak acids and weak bases, you can come into contact with more with less of a chance of having issues of corrosion. So remember what this means. So that double arrow, that means that this is reversible. And remember, that means that when you start off with acetic acid, so if you have pure acetic acid, no water at all, and you add water, some of the acetic acid molecules, that CH3COOH, some of those molecules begin to break down into ions. But eventually you reach this point where the forward reaction and the reverse reaction are equal. So that means that the amount of acetic acid molecules forming ions is equal to the rate of the ions reforming the acetic acid. Does anybody remember what that's called? That happens until you reach equilibrium. So if you start with pure acetic acid and you add water, then the forward reaction will begin to occur. But at some point, some of those ions will begin to reform back into acetic acid molecules, and you'll end up having this balance. So remember that isotonic, how it was like the equal salts that we talked about in the blood cells, trying to maintain this equal balance. Well, that's what happens when you start a reaction that is reversible. Eventually, you end up with products and reactants all together in the same container. So I'd start with pure acetic acid, and the forward reaction would take place more, but eventually you would have some reverse reaction, and it would end up equaling the forward reaction. And that is where you would have 95% would be unionized acetic acid molecules, 5% would end up being ionized or forming those ions. That's equilibrium. So strong acids and bases don't do this. Strong acids and bases just form 100% ions. Remember those strong electrolytes and how you drew them. Weak electrolytes, though, have that ability to reform, to have a forward and reverse reaction and create this balance of reactants and products all together in the same beaker or container. One that is a weak base, it's really strong smelling, but it is a weak base, is ammonia. So NH3. So if I start off with NH3, if I add water to it, that NH3 acts as a proton acceptor and forms the hydroxide ions. So NH3 is a base. Remember that the bases take on hydrogen ions. So notice NH3 went to NH4 plus. The hydroxide ion is produced, characteristic of the base. But eventually, I start to have a reverse reaction that occurs. And ultimately, in the container, all four of these compounds exist. So all of them exist in a ratio. There's a lot more ammonia compared to the ammonium ions that are present, but all of those would be present in sort of the one system at equilibrium. It's because it's a weak base. So weak bases, weak electrolytes do this. Now, if I take a strong acid and a strong base and I add them together, strong acids make those hydrogen ions that are very reactive. Strong bases make those hydroxide ions that are very reactive. Put them together, though, and you end up with a salt and water. And so this one's a great example because hydrochloric acid and sodium hydroxide. So hydrochloric acid is like stomach acid. Sodium hydroxide is like that lye, what we use to make soap. But if I take these two and mix them in equal molecules, I end up with sodium chloride and water. So I end up with just salt water. Is salt water reactive? No. So this neutralization reaction, it takes the very reactive molecules and converts them to extremely stable solution. Where there's no acid or base, it's just a neutral salt dissolved in water. An example of this is what we did in lab with antacids. So in lab, we actually took like Tums, Rolaids, ground them up and mixed them with hydrochloric acid to monitor how well they neutralized that stomach acid. So antacids are actually bases. So like ant is sort of like against. So an antacid is like the opposite of an acid. So instead of just calling them bases, that's where the name kind of came about. An antacid is really a weak base. You would not want to drink sodium hydroxide. So if you had stomach indigestion and you wanted to neutralize the excess stomach, you don't want to ingest a strong base because that would cause damage to your mouth, esophagus. It would cause damage to tissues because remember, strong bases are very reactive. So instead, they use a weak base. So a weak base just means that it doesn't make a lot of hydroxide ions. It doesn't act as a strong proton acceptor. It's not as reactive, but it'll still react. So in this first one, this one's showing like milk of magnesia is made of magnesium hydroxide. That's MgOH2. So that milk of magnesia, when it comes in contact with stomach acid, it does like a double displacement. So if you think of Mg and the OH2 plus the HCl, so it is really the outside pairs and the inside pairs that end up combining. So H and OH always make H2O. And then the metal and the non-metal on the compound pairs form the salt. So this is where you end up with the Mg and the Cl. So remember that magnesium's in group 2, so it's a +2 charge. The chlorine's over in group 7, which gives it that -1 charge. And so you know the formula by doing the swap. So remember that the charge on the metal tells you the number of nonmetals, the charge on the nonmetals tells you the number of metals. So that's how they end up with the formula of MgCl2. The H and the OH, no matter what the combination, like notice in this one I have 2 OHs and only 1 H, doesn't matter. H and OH will always combine and form H2O. So the inside, the H and the OH will always combine to form water. The outside pairs of the metal and the non-metal make the salt. So you would go back and like balance it, but it would always end up being this sort of outside pairs, inside pairs. Whichever one's the H and the OH becomes water. The other pairs are what form that salt. Metal goes first. So one that's kind of interesting, and in fact, we found like that milk of magnesia was like really strong at neutralizing excess stomach acid. It changed the pH the most out of all the ones that we tested. But sometimes you'll take like a Tums or a Rolaids or generic antacid, and those are typically got some carbonates in them. So one interesting characteristic of antacids that have a carbonate is when these react, they don't just make a salt and water. The carbonate, that CO3 part of the Tums, breaks off and forms carbon dioxide. So if you have acid indigestion, you eat a couple of Tums, chew them up. They're kind of gritty tasting, kind of grainy tasting. So you chew them up and swallow them and wait a little while. 10 to 15 minutes later, what do you commonly do? If carbon dioxide is produced in your stomach, burp. Yeah, it's a gas. Okay, so that would be like a common like reaction that you may have, is you may notice that you actually burp a couple of times. That's actually the carbon dioxide that's produced in the stomach as that carbonate is neutralizing the excess stomach acid. So when you have reactions between molecules that form a reversible reaction, so like those weak electrolytes that we talked about, if you have this reversible reaction, then that means eventually you end up with all of the reactants and products present in the container in some kind of combination that don't have to be 50-50. So this one shows like 1 nitrogen plus 3 hydrogens reacts to form 2 NH3s, right? So that's what that balanced equation is telling you, just the number of each. But if I started off with 100 molecules of nitrogen and 100 molecules of hydrogen, they will react and begin to form NH3. But at some point, the NH3 molecules will begin to break back down into their nitrogen and hydrogen, and eventually you reach the equilibrium. So the equilibrium is just when the rate of the forward reaction and the reverse reaction are the same, right? So when the forward reaction is equal to the reverse reaction, then there's going to be no change in the reaction. The amount of reactants and products stays kind of constant. So that's what happens in equilibrium. So anytime you see a reaction where the arrows go both directions, then know that it's going to end up having some kind of balance of reactants and products when you reach that point of equilibrium. Weak acids, weak bases, even other weak electrolytes. Strong electrolytes aren't going to do that, because strong, if one of the criteria is you've got to see the arrow going both directions. Okay, so if the arrow goes one direction, then it just goes to finish and it's done, right? So that's like burning the charcoal briquettes, one that we talked about earlier in the semester. Arrow goes from left to right. Once the briquette burns, you can't remake it. It doesn't go back and reform the briquettes because it becomes carbon dioxide and water vapor. It disappears.
So if it's reversible, it's always going to be like weak acid. Or
It's like reversible reactions are typically what you see with like a weak electrolyte, not necessarily a weak acid or base, but a weak electrolyte. Or it's a reaction where the reactants in the products, remember when we did that graph where I talked about exergonic and endergonic reactions? So if the reactions, the energy of the reactants in products are really similar, then the forward and the reverse reactions are not that much different to go from one direction to the other. So like in this one, so nitrogen and hydrogen by themselves are pretty stable, but they're also pretty stable when they combine to form NH3. So since the energy to form and the energy to break are close, that's what allows this reaction to be reversible. Whereas when you have reactions where you have to put a lot of energy in to make the other, then those, it's going to be a little bit different. It's typically not as reversible as one where we have similar energy amongst reactants and products. So we had a French scientist that studied this, and this was like his big thing, is he like studied reactions that were reversible and tried to decide, well, what happens in this reaction if I get a reaction to what they call equilibrium? What happens if I change the criteria in this reaction? So for example, if you have this container, and we'll just say that this container has equal amounts. So we'll put 4 nitrogens, 4 hydrogens, and 4 NH3s. So we'll say that at equilibrium, they're all 50, 50, 50. So they're equal. NH3, NH3, NH3. Okay? So I have 4 hydrogens, 4 nitrogens, 4 NH3s in this container. So it was like, okay, well, what happens if I add nitrogen? Okay, because at equilibrium, the forward and reverse reactions have created this like stable system. So what happens if I add stuff to it? If I add nitrogen, so now coming in, we can put them in a different color. So what if I just throw in some extra nitrogen? Now I don't have the balance, right? So now the ratios are off. So the system or the container, the reaction will actually try to shift to restore balance. So how could I make the balance better? If I add 3 nitrogens, okay, so if I could take some of those nitrogens and run a forward reaction, that will make some of those nitrogens into NH3s and bring the ratio closer to being balanced. So what I have to do is take this nitrogen and 3 of the hydrogens, because I have to use 3 hydrogens in order to do it, and use that to make an NH3. So now do you see that the numbers, although they're not exactly the same as they were initially, now they're a little closer to being in this ratio, this balance. So what he found is anytime you add something to a reaction that's at equilibrium, the reaction always shifts away from whatever you add. It doesn't matter if it's a reactant or product. The reaction always shifts away from whatever you add. And so one way that I kind of remember it is if you add, it shifts away. So they're both A's. So if you add something, the reaction shifts away. So if I added product, the reaction would shift in reverse. If I add reactant, the reaction would shift forward. And the goal is to restore balance. So another way that I think of this is I think of it as being like a seesaw, right? So like you've seen kids like on a seesaw. So the little pivot's right in the very center and you have like 2 equally sized people about the same distance apart and they're balanced, right? So they can actually like completely balance and not one's not lower or higher, they're exactly the same. But then what if one kid goes and jumps over onto one side, then you know it goes down because there's more weight on one side. So the only way to balance that is to try and shift, adding more to the lighter side to bring it back into that balance. So it's the same thing here. If I add weight, the reaction has to shift away from whatever I add in order to try and bring that balance back into play. He found the exact opposite, though, if he took something off. So if he took away reactant or product. So if I took this and I was like, oh, well, I am going to remove, I didn't want to remove hydrogen. I was just going to remove nitrogen. Well, they removed hydrogen in the example. So keep the N2. But if I take this hydrogen out, pulling out a hydrogen, if I take this hydrogen out, now there's no hydrogens. So it's like the reactant side now has lost some. And so what he found was that the reaction always shifted towards whatever was removed. So if you remove reactant or product, doesn't matter which one, the reaction always shifts towards what was removed. So in this one, if you started pulling hydrogen out, the reaction shifts towards the side with the hydrogen, and in this case, that would be in reverse. So they're sort of the opposite. Now this happens only if you're talking about a reaction that's at equilibrium, and you add or you remove one of the components in the reaction. But now, if I added water to this, nothing would happen because water's not part of the reaction. It's only the things that are part of the reaction that come into play. So another thing that he looked at was he looked at how temperature came into play. So he said, well, what if you change the temperature of a system that's at equilibrium? If I change the temperature, I'm either adding or removing heat energy, right? So if you heat it up or if you cool it down, he found that it depended on what kind of reaction it was. If it was an exothermic reaction, so everybody remember this means that heat's given off. Exothermic, heat is a product because heat is produced in the reaction. If heat is a product, you just treat it exactly the same. So which direction would it shift if I added heat to this reaction? And this arrow should go both directions. To the left. It's just like I'm adding product. If I added heat, it's the same as if I'm adding product because heat's on the product side. So the reaction would shift to the left, shifting away from whatever I added. But if I took this sample and I chilled it, then that would be like pulling temperature, pulling heat away. So if I removed heat by lowering the temperature, which direction would it shift? To the right. Okay? All it's trying to do is just to try and restore that balance. So if I have one, like what happens in that formation, NH3 plus H, it's not actually that one. It is NH4Cl. This is, have you ever had a cold pack? Like that one where it's like these crystals inside and there's a little bubble and you smack it and shake it and it gets cold. Have you ever used those? Okay, so that's actually ammonium chloride. The crystals that are in the little smack bag, you can kind of feel them. They're kind of like, feel like bigger than salt. They're like kind of chunky crystals. And then in the little bladder, there's like a little packet inside that actually just has water in it. So the sodium, ammonium chloride, this is a solid. The water is just the liquid. When you mix it together, it is very endothermic because it feels cold as it reacts. So as that ammonium chloride hydrates and forms NH4 aqueous and chloride aqueous, as it dissolves, it actually absorbs heat. So that's why they use it as a cold pack. So in this, you break it, you shake it up, and it gets cold, and it'll stay cold for hours. So it's absorbing heat energy as that ammonium chloride dissolves. So if I took this and I put this like in a warm place, which way would the reaction shift, forward or reverse? So if I add heat, heat is a what? Is it a reactant or a product? So heat is on this one, heat's a reactant on this one, right? Heat is on the left, and so the reaction will shift in this direction. If I remove heat, so I put it in the refrigerator, then reaction is going to shift towards the side with the heat. Whereas with the first one, if I add heat, which way did you say the reaction would shift? It's going to shift to the left. So the reaction shifts away from whatever was added, away from the side of the heat. So you could say that the reaction shifts in reverse, or the reaction shifts to the left. So reverse to the left or towards the reactants, all saying the same thing. Shifting forward means towards the product side. So I brought a demo to show you this. And so probably be one. You want to stand over here and you can be the other person. So what I've got is I have two bins, two little tubs or containers. So we'll say one is reactants and one is products. So whenever you start a reaction, you always start with all the reactants, right? Okay. So if I start with 100% reactants, okay, so that's always like the very beginning. And I don't know if you can see, I hope you can. If you can't, you can come stand up and come stand over on the side just to look. Okay, so what you're going to do is, so this is the forward reaction. Okay, so the forward reaction, so you see the amount of blue liquid that gets picked up, now that becomes product. Okay, but if it's a reversible reaction, now you have a reverse reaction. And so notice that there's like a drop in there. So initially, do you see that the reverse reaction is very, very low? So then again, forward reaction is pretty big into this one. And then the reverse reaction, there's a little bit more, okay? So gradually, you go back and forth here. So you go do one and you go do this other one. And so what you want to do is, the rules are no scooping. So you're not trying to like scoop water up because it's just a reaction. Rates take place at uniform levels. Don't hurt yourself though. Okay? So no scooping. Just set your beaker down, take it up, dump it over there, and then you have to wait till she does hers. So you do one, then you do one, and you do one. So you just keep doing those. So notice in this, my beakers are the exact same size. So what do you think is eventually going to happen? Okay, in equilibrium, what will that mean? Yep, the amount, two beakers will hold the exact same amount, right? So then the amount I pour forward, the amount that comes back, they're going to be exactly the same. Since the beakers are the same, what do you think is going to happen to the levels of the water in those two containers?
Is this also an example of osmosis?
No, well, all reactions start, you always start with only reactants, right? So that's why I just poured everything into the one, okay? If this was a strong electrolyte, then all that reactant would form product and you'd be done. But since this is a reversible reaction, Riles is the forward reaction, Abigail's the reverse reaction. What do you think? Like dip both of yours and hold them up side by side and we'll see. Stop trying to scoop up. Hold them up side by side. Not exactly the same. Keep doing a few more. Okay, so forward, reverse, and the kicker is just lower your beaker, pour it in, lower your beaker, pour it in. But do you see that they kind of look like they're starting to be about the same, the levels? So everybody always thinks that equilibrium means there's equal amounts on both sides. But what about this? So now I want you to use that beaker, and I want you to use this beaker. Okay, we're going to start it over. So we're going to put everything back on the reactant side. So now she's got a 400 mil beaker and she's got a 100 mil beaker. So go ahead, forward, reverse, same thing. So notice in the first, the 400 mil beaker holds a lot. The little 100 mil beaker, not so much. Okay, So just dip it all the way to the bottom of the pan, pour it. Pour back. What do you notice about the reverse? Is it increasing a little? Okay. So what do you notice about the levels? Are they looking like they're getting the same?
I think so.
Keep going. So which beaker has kind of got a limit as to how much it can pick up? The little one, right? The little one can't pick up but so much. It can only hold a max of 100 mils. So even if it was filled, it can never really move more than 100 mils. So that's going to end up being like the limitation. When we get to equilibrium, they're both going to be moving about 100 mils back and forth, back and forth. So what do you think? Looking at the volumes, are they the same? Which one? Which one looks like it's starting to have more? The product side. So equilibrium does not have to mean that you've got exact amounts of all of them. It doesn't have to mean that there's 50-50, 50% products, 50% reactants. It just means that the forward and the reverse reaction eventually reach this point where there's no net change. And so if you look at it, okay, so dip yours and hold it and tell me, and you dip yours and tell me about how much you think they've got. That one, I'm looking at the beaker on the side. Okay, so about 60 and 75. Not exactly equal, but pretty close. So you can see that's going to end up being like the limitation. So the forward and reverse. No, don't be drinking it. We're just going to turn your blue. You can just leave them in there. I'll wash them afterwards. Okay? So now I'll ask you a question. You tell me, like Le Chatelier, what do you think would happen to this reaction if I added water here? If I added water to the reactant side, okay, well, I mean, I'm adding the same stuff. So if I dump this, now if I start to do this, which reaction is going to have a greater volume? Forward reaction or reverse? Forward, right? Because I just dumped more water into this tub. So I would expect this beaker to move more liquid to the product side, but eventually what would it do? It would balance out, okay? So when I add the forward reaction, if I add reactant, the forward reaction would get greater until it reached equilibrium. Well, then what would happen if I took this and I took some of it out? So that's the same thing as removing reactants. So now when you look at it, you're like, oh, it's not the same. So if I remove reactants, now which reaction is going to move more? The little beaker. From the product side going in reverse. So that's what he found. He was like, well, if I add reactant, the reaction is going to shift, making more product until it reaches equilibrium again. If I remove reactants, the reaction is going to shift towards whatever I removed, causing the reverse reaction to become greater until it restores equilibrium. So his sort of summary. So notice he said in concentration, if you're looking at reactant or product, if I add reactant, right, so that's adding it to the left, the reaction shifts to the right. It shifts away. If I add product, which would be to the right side of the reaction, then they find that the reaction is going to shift in reverse or shift to the left, again, shifting away from the product side. If I remove reactant or if I remove product, the reaction always shifts towards whatever I removed. So reaction's on the left. If I remove reactant, then the reaction shifts towards the reactant side. If I remove product, which is on the right side, then that causes the reaction to shift to the right. So this is sort of the same that he found. Now, temperature. Raising, lowering the temperature, adding heat, removing heat, all different ways of describing. But what you have to remember to look at is look at the reaction and figure out if it's an endothermic reaction, then you know that heat or energy is on the left. It's a reactant. Endothermic, energy is a reactant. So if I add energy, reaction shifts away from the side where the energy is, which would be to the right. If you lowered the temperature on an endothermic reaction, it would cause the reaction to shift towards the side that has the energy or heat. If it's exothermic, though, then remember exothermic means that energy or heat is a product. Because exo means to come out. So in exothermic, energy is released. Endothermic, energy is absorbed. So those, notice that they're opposites, but you just have to think, I just think, okay, energy is either a reactant or a product. If it's an endothermic, energy is a reactant. If it's exothermic, energy is a product. And then just treat it just like a reactant or a product as above. So here's one. So you do these. So here's your reaction, NH3 plus HSO4 negative plus heat will make NH4 plus and SO4 2 negative. So notice you got the arrow going both directions. If I have this reaction at equilibrium, which way will the reaction shift if I add NH4? Nope. Find NH4. So if I add NH4, the reaction shifts away from it. So that means that the reverse reaction will occur. So then removing SO4 2 minus. So find that. So here I'm removing. So if I remove SO4 2 minus, I don't know what that word is. So if I remove this, then the reaction always shifts towards whatever I remove. So forward reaction will occur. What if I add heat? Forward or reverse? If I add, anytime you add, it's always going to shift away from whatever I add. So notice if I added NH4 plus, reaction shifts away from where NH4 plus is. If I add heat, reaction shifts away from the side that has heat. So that would cause the forward reaction to occur. Then, what if I remove HSO4 minus? So here, you got to find HSO4 minus. Whenever you remove something, the reaction shifts towards the side you removed it from. So that's going to cause it to come back this way, so reverse. And then the last one, what if I add NH3? So if I add NH3, the reaction shifts away from whatever I add, so that would cause the forward reaction to occur. So this happens once you get something at equilibrium. If you shift or change any of the reactants or products or the status of its energy, if you add heat or remove heat, that will cause a shift in that equilibrium. So when thinking about acids and bases, these do this as well. Acids and bases that are weak acids and bases have this ability when they react to form an equilibrium system. So in this one, if I take acetic acid and water, so that's CH3COO plus H2O, that's the beginning. When they react, they go so that about 5% becomes products, but about 95% remain as a whole. So that means in the beaker or container, I've got all four of these things. They exist in equilibrium. So that means in the forward reaction, you can define what is the acid in the base. So you got to go back and remember that the acid is always the one that does what with its hydrogen ion? Does it gain or lose? Lose. So acids lose H+, bases are going to gain. So if you take and follow this one, find its pair, Do you see that it loses an H? So it goes from CH3COOH to CH3COO. So you see that it loses its hydrogen ion. So it loses H plus. That's an acid going in this direction. But now look at the product side, because remember that you end up with forward and reverse. So in the reverse of this, CH3COO minus converts back into CH3COOH. So in the reverse reaction that I'll color in red, what happens to CH3COO minus? It gains a hydrogen. So if it gains, that makes it a base. So that means, so on this side, I have the acid, its pair is the base. The product side, they name them by their conjugate so that you can determine which is the acid and which is the base. That's always on the reactant side. But in the reverse reaction, you can identify the conjugate acid and base, which really just determines what happens in the reverse reaction. So looking at H2O, and going in this forward reaction, what happens to H2O? It gains a hydrogen ion. That makes it a base. But now if I look at H3O plus, looking at H3O plus and going in the reverse, do you see that it loses? And so losing hydrogen ions is characteristic of the acid. So that is why it is an acid, but they'll call it the conjugate acid. So acids and bases are always defined on the reactant side. Conjugate acid and base are always defined on the product side. That's one thing to remember. Acid and base is on the reactant side. Conjugate acid and base is on the product side. But the other thing you can remember is that the acid always becomes the what? And it's not just the base. The acid always forms the conjugate base on the opposite side, on the product side. And the base on the reactant side always forms the conjugate acid. Now this only happens in these reversible reactions, so you don't see it if it's just a neutralization reaction, but this happens in a reversible reaction, so I'm really defining what happens in the forward and then also what would happen in the reverse. You got those? Okay, so let's practice a couple of them. We'll do this one first, and I'll just walk you through it. So CH3, NH2. First, going across, identify CH3NH2 becomes CH3NH3. So it has gained a hydrogen ion, that makes it a base. So then I know on the opposite side, that product will reform the base, so it is, by losing its hydrogen ion in the opposite direction, so that's called the conjugate acid. So the base, which gains a hydrogen, will then turn around and lose a hydrogen in the reverse reaction, which is why they call that pair a base and its conjugate acid. H2O, water in this one, loses its hydrogen ion when it forms the product. So it goes this direction and forms that hydroxide. That's why it's an acid. But then if I flip and look in the opposite direction, the hydroxide ion is going to gain the hydrogen back, so it acts as a base. But since it's on the product side, you're going to call it the conjugate base. So bases form the conjugate acid, acids form the conjugate base. When you're looking at an acid-base reaction where they're weak acids and bases, where they form in equilibrium. That way you know there's forward and reverse reactions that occur. So you tell me, looking at this, HCN plus NO2 minus forms equilibrium with CN minus and HNO2. So first thing to do, find the pairs that look the most alike. So with HCN, what looks the most like it on the product side? CN minus. Everybody agree? Okay. So HCN and CN minus look similar. So they're going to be our pairs. That's the first pair. And then looking at the second one, NO2. NO2 and HNO2. Agree? They look like they're similar, so they were beginning and ending pairs. So now those I know are my acid-base pairs. So the next thing is, what happens to HCN? It loses a hydrogen ion. So if it does that, it's a acid. That means that CN minus is the, what kind? It's a conjugate. So on the product side, you've got to put conjugate. It's the base.
How did it lose it? Never mind. I just figured it out. Never mind.
So it's really the hydrogen gets transferred to the other one.
Sorry.
It's okay. All right. Now look at NO2 minus and its product. What happened? Can you everybody see that it gains? So this gains, the NO2 minus is the one that gains the hydrogen ion. If it gains, it's a base. So that means its pair on the opposite side must be the conjugate acid. Do the next one. So I find it's easiest if you like connect the ones that are similar. Then figure out if it lost or gained. Did it increase or decrease in its hydrogen ions? If it loses a hydrogen ion, then it's an acid, and you know that its pair is then the conjugate base. If it gains a hydrogen, it's a base, and that way you know that its pair is the conjugate acid. Okay, so first one, NH3, what did you think was its closest pair? NH4 plus. And it's not always necessarily going to be the first one in the first one. Just make sure that you look at the formula because that's how you pick them out. So then the second one, HSO4 is SO4 2 minus. So everybody agree that those look like they're the most similar pairs. So now looking at NH3, what happens to it? Gains, so it is a base. So that makes the NH4 plus the, and I'll put CONJ, but that's conjugate. Okay, then looking at HSO4 minus, that is to SO4 2 minus. It's an acid because it loses its hydrogen ion. It's the acid, so that means now SO4 2 minus is the conjugate base. Okay, so the big thing you got to remember, like if it loses a hydrogen ion, it's an acid. If it gains a hydrogen ion, it's a base. And then on the opposite side, in an equilibrium reaction like this, the acid always forms the conjugate base. The base always forms the conjugate acid. So here's the question. If this reaction is at equilibrium, so this NH3 plus HSO4 minus reaction, if it's at equilibrium, you tell me which way will the reaction shift if I add NH4 plus. Forward or reverse? Reverse. Okay. Right? So if I add product, the reaction shifts away from the product side. What if I remove SO4 2 minus? So if I remove product, the reaction shifts to replace it. Okay? When you remove something, the reaction always shifts towards whatever you removed. So what if you remove NH3? Reverse. Because it's going to try and shift towards the NH3, which is on the reactant side. So I have to shift it to in reverse. And what if I add that HSO4 minus? That'll be the forward. Okay, so we'll do a couple more of those ones in terms of practicing. And then I've got these ones as well. These are on, if you printed your PowerPoints, these are on your PowerPoints, but I actually sat down and typed them out because they were handwritten. So you should still see those ones. We'll work on those ones next time. I just want to introduce one last thing. So what they found in doing calculations is, remember when we had distilled water and I put it on the light bulb thing and it didn't light up? And so I was like, well, water is not an electrolyte because water doesn't light up at all. But they found if you have two water molecules that they actually can ionize a very, very, very small amount. So if we have like 1 mole per liter of water, okay, 1 mole per liter of water, and we measure the actual amount of dissociation that water can do, about 1 times 10 to the minus 7, which in they put it in 0.00000. 1, 2, 3, 4. Yep. 1. About 1 times 10 to the minus 7th moles of those water molecules would actually form ions. Now that's so small that it can't carry an electric current. So that's why it didn't light up the light bulb. So they said this is an extremely low amount, okay? An extremely low amount of ions, but it does happen. And do you notice that there's hydroxides and hydrogen ions that are formed? So they said, oh, there's acid and base in the water, and they're equal. And so we can make this now, since the acid and base content is equal, we can say that this is neutral, right? Because neutral means it's not an acid or a base. It's where the amount of acid and base is exactly the same. So we knew that water molecules were neutral. So then this is what water is, because the amount of hydronium ions or hydrogen ions is equal to the amount of hydroxide ions. So then by definition then, something that is acidic has more hydrogen ions than hydroxide ions. So can you see that on that left side? So things like the lemons and the vinegar, the acids, hydrochloric acid, they have more H3O plus hydrogen ions than they have hydroxide ions. And so they're like, there's this category. Then there's a category where we have more hydroxide ions than hydrogen ions, and that's going to create something that is basic. So if we know that there is 1 times 10 to the minus 7th molar, that is the concentration of hydrogen ions and hydroxide ions in water, and we make that the neutral point, we can go down, and as we go down, we're going to increase the amount of acid, which means that our decimal place gets smaller. So this ends up being in the 1 times 10 to the minus 5, 1 times 10 to the minus 6, 1 times 10 to the minus 3, because it means there's more and more acid that's present. So things that are acidic are on the low end of the scale. Things that are basic are going to be on the high end. And this is where the pH scale came about. So if water is neutral at 7, we can have this scale go up to its highest point of 14 and down to its lowest point of 0, with 7 being exactly in the middle. So that's sort of the natural pH scale of 0 to 14. Anything below pH of 7, this is an acid. Anything above pH of 7, that's a base. And it's really based on the concentration of those exponents. So acids typically have smaller exponent numbers because they have more concentrated hydrogen ions. Bases end up being like 1 times 10 to the minus 8, 1 times 10 to the minus 10, 1 times 10 to the minus 12. The concentration gets lower and lower and lower, which causes those exponent numbers to get bigger. So next time we'll just review some of the conjugate acid and base theory, a little bit more of equilibrium, and then we're going to do pH buffers and finish out this chapter. If you didn't turn in your take-home exam, please make sure you just stick it on the pile on your way out.